So now I have these two integrals right here with a common denominator. Now I need to get these denominators into a form so that I can do a better substitution on these, and this is where completing the square comes in. I really want to get these in terms of perfect squares so that they'll be a lot easier to work with. So there's two ways to do something like that. We have u squared plus 1 over u squared. So I notice if I could just get these square signs to go away, that's how it would set up to be a perfect square. Ultimately, I want to end up with something like u plus 1 over u plus or minus something equals this. So what do I have to add or subtract in order to make these two sides equivalent? Well, let's take a look at this. Let's factor it out. So I have u plus 1 over u times u plus 1 over u. Let's see what it actually equals. Foiling it, u times u is u squared. 1 over u times u is 1. U times 1 over u is again 1. And lastly, 1 over u times 1 over u is 1 over u squared. So this equals u squared plus 1 over u squared plus 2. So it's almost what I have here, except that it has an extra 2 in there. So when I take this and square it, I have an extra 2. I have 2 more than what this has, so if I really want to make them equivalent, I have to subtract out 2. I have to add a negative 2, and it would be better to write that as subtraction. This right here is equivalent to u squared plus 1 over u squared plus 2, so if I subtract out 2, then I get equivalency. So this is equal to this squared minus 2. On the other hand, there's another way to do this as well, because we are, after all, squaring this. I can also say that this equals u minus 1 over u squared, plus or minus something. Let's FOIL that one out. U minus 1 over u times u minus 1 over u. U times u is u squared. Negative 1 over u times u is negative 1. U times negative 1 over u is again negative 1. And negative 1 over u times negative 1 over u is positive 1 over u squared. So once again, I have u squared plus 1 over u squared, and this time I have minus 2. So this is equal to what I have here, minus 2. So if I want to get equivalency, that means I have to add 2. So I have 2 ways right here to express this, completing the square. Now I'm going to use both of these to my advantage in evaluating these integrals right here. I'm going to set one of them equivalent to this and one of them equivalent to this. Which one we choose depends entirely on the situation and is going to be simply a matter of which one makes it most convenient to do our substitution. So in this case, I'm going to take a look at my first integral right here, which is 1 plus 1 over u squared. And this time, for this one, I'm going to take my denominator right here, and I'm going to express this as u minus 1 over u squared plus 2. I'm going to choose the second of my 2 options, and of course this is du. So now, after all this manipulation, what have I accomplished here? I'm going to do another substitution. Nobody ever said we had to stop at one substitution. So I'm going to do u substitution again, but I've already used u. So let me just define a new variable here. Doesn't really matter what I call it. Let me call it s. And let me say, let s equal this right here, equal u minus 1 over u. If that's true, then ds differentiating with respect to u becomes 1, and minus 1 over u becomes plus 1 over u squared. So now I have expressions right here in terms of a new variable. So when I plug that back into here, I notice that my entire numerator right here, forgot to put the du here, my entire numerator here is just equivalent to ds. And my denominator here is equivalent to s plus a 2. So this is precisely why I've been manipulating this and setting this up all along, so that I can do a convenient substitution that will just capture everything I have right here. So this integral right here becomes ds over s squared plus 2. A much, much easier integral to work with. Now this right here is a classic case of trig substitution, which is something we've covered briefly.